welcome to my talk, as he said, when idioms become bottlenecks. I'm excited to be here today, but if I seem a little spacey, it's because my body decided to only let me get 3 interrupted hours of sleep last night. So the plan. First, I'm going to introduce myself on the next slide, and then I'm going to talk about some Go idioms, what they mean in cases where it may make sense to actually break these idioms. And in this breaking the idiom process, I'm going to describe my epic attempt at creating a message queue system, where it was good, where it was bad, and then rant a little bit about what I'd like in Go to make that easier in the future, and then wrap up with a tiny summary. So, about me. I've been using Go since January 2013, so that's just a couple months before the 1.1 release. I enjoy speeding up hotspots and programs. And I've been working at Fastly on all stats pipelines. That's sort of been my main project for the last 2.5 years, but I've been there a bit longer than that. So let's talk about some idioms. Rob Pike gave a talk a few years ago where he rattled off a bunch of Go proverbs that Gophers live by. So for example, with the Unsafe package, there are no guarantees. If you use Unsafe in your code, likely it's going to be unsafe. Clear is better than clever. If you have unmaintainable clever code that does something awesome, you should likely make that code clearer, even if it comes at the expense of some performance. And then channels orchestrate and mutexes serialize. Historically, before Go, we shared data across threads with mutexes, which are complicated and you'd probably end up getting them wrong. In Go, this sharing of data can be done with channels, and I don't think I need to really talk about those. Mutexes still exist to ensure serialization of code execution at some points. They are still necessary. But these proverbs beget idioms, so if unsafe is, well, unsafe, then you should never use it. And while we're at it, since assembly is lower level, we should likely never use that either. It's too complicated. And we definitely should not write complicated code, because it will likely be too hard to maintain, hence the proverb. And lastly, since channels make communication easier, we should always just spin up Go routines and communicate with channels when, with a little bit of more complicated code, mutexes or something else would read cleaner. However, idioms can be broken. Unsafe can be safe if used correctly. It may be a good idea to use assembly, and complicated code is actually sometimes worth it. And channels, although quite magical, can have alternatives if we know what we want and we're willing to give some things up. So the idioms that I've been talking about are what my talk revolves around. So let's see how we can break them. To start, unsafe. It's there in the title. It's not safe. Don't use it. But one of the most common patterns that you're likely to run into, or maybe have even used in your code yourself, is to convert a slice to a string without any garbage overhead. A slice in memory is laid out as a 3-word size struct, and what I mean by a word is it's something the size of a pointer. So on a 32-bit system, it's going to be 4 bytes. On a 64-bit system, it's going to be 8 bytes. So anyway, slice is 3 and a string is 2, and they start with a data, length, and capacity, whereas a string is just data and length. What we can do is blindly say that our slice is actually a string and use it without copying the slice to a string, obviating the garbage, eliminating overhead. I've used this in little tiny sections of my code where I need to convert slices to strings all the time, and it has actually saved me a lot of performance. So going in the opposite direction, it's slightly more complicated. As I just said, a slice has 3 words and a string has 2. So if we want to use a string as a slice, we would be pulling an extra word in. And this extra word, if at the end of an operating system page, could crash your program when a moving garbage collector moves your string and attempts to actually move a slice and moves an extra byte. However, if we start with an existing slice and copy all the values into the struct manually and set the capacity as well, the slice will have completely valid values. This will allow us to use an existing string as a byte slice in a function that does not modify the slice without creating garbage. I have used this, one of the hotspots that I've used this is by converting string service IDs to a byte slice for use in the Go murmur 3 hashing algorithm. And lastly, let's talk about unsafe versus interface. Unsafe is tricky to use, and it's unreadable, as evidenced in that last slide. An interface is not tricky, and it is highly readable. That's why it exists. However, in the guts of a program, if we want to pass around generic heap-allocated data without allocations, it seems to be the case that we can use an unsafe pointer. My interpretation of the unsafe documentation, which is complex, is that an unsafe pointer is a reference, the same way an interface sort of is. But using an interface forces an allocation of two words. Thus, an unsafe pointer will not create garbage and will speed up your code in little tiny hotspots. Now this last instance is highly unlikely you're going to need this, but it's possible. Interface says nothing, but it does allocate. We can avoid that in high-performant code. So really, the last few slides simply point out that unsafe can be useful and safe if used correctly. It's unfortunate that the documentation around unsafe is probably the most confusing part of it, and it's also unfortunate that everything in the language actively discourages you from using unsafe in all instances, and they sort of like wish they didn't have to expose it at all. Occasionally, in specific instances where you control the API and the internals, it may be beneficial to use unsafe safely. So, assembly. I'm not really going to go into assembly in Go. There's a later talk that actually does go into it. It's simply too much for mine. But I will describe one instance where we used assembly internally for great profit. Internally, oh man, that format's a little off. But internally, we have a program that encodes segments of data into various formats. And a couple of months ago, we were requested to come up with a format that had encryption. And what happened was, because of our necessary usage of the Go crypto API, it forced a ridiculous amount of allocations compared to all other encoding formats. This effectively meant that the encryption encoding format could DOS the rest of the program if a customer specifically hammers on that one. And we could not have any predictable guarantees about this new format compared to the rest because it was completely different. A colleague of mine took a look underneath the hood and investigated why these allocations were necessary, and then ended up stripping down and implementing his own version, the minimum of what we needed of this encryption in assembly, rewriting it in such a way so as to avoid allocation. His implementation resulted in bringing down the allocations for encrypting encoding by 200x, with a side benefit of a 7x reduction in CPU. So sometimes informed assembly is a good idea. Assembly can be useful. Hand-rolled assembly for obvious things are likely unnecessary, and now with the new SSA backend, compiler backend, and everything else, you'll probably end up writing something worse than what could be done for you. But in some instances, it can be useful. You just have to know where to use it, and pprof can help you. Finally, onto our gateway drug, everything that is Go, the channel. Channels do a lot. They provide a bounded, meaning sized, first in, first out queue. Using a channel is linearizable, meaning if in queue A finishes before in queue B, then we're definitely going to dequeue A before we dequeue B. We can use multiple channels in select statements and let magic happen. And they support multiple producers and multiple consumers on channels at the same time. So frankly, channels are just magic. Additionally, channels are really good. There used to be some rumblings, I haven't seen any lately, about how anybody could just have an array, surround it with a mutex, and have much faster performance than a channel. But what doesn't make sense is channels internally are implemented as an array, surrounded with a mutex, with many runtime fast paths that check to see if it even needs to fall into that mutex. So it's simply not possible to implement a channel-like thing in Go, providing what a channel provides, that will be anywhere near as good as a channel itself. However, as I just mentioned, channels use mutexes. Mutexes are not inherently bad. They're really fast. However, in a highly contended scenario, mutex performance is unpredictable. We simply cannot know when many actors are trying to grab a lock at the same time how they will perform relative to each other. They'll sleep and wake up at unpredictable times. It's just simply unknown. This means that in a heavily contended scenario, we can predict that channel performance will fall apart. So Chan does a lot, and sometimes we do not need so much. Can we do better? And before I dive into that, it's worth it to ask what even is better. As I was talking about on the last few slides, predictable latency is a good thing to aim for, and we have this theory that since channels are implemented internally with the mutex in a highly contended scenario that fall apart, if we come up with something to eliminate these mutexes, we should have better, more predictable latency. But there are other candidates for better, like less CPU or higher throughput. Our current goal is to remove mutexes, and we have a prediction for what will happen, so let's get on with it. And I have to apologize, it's going to switch from black to white because the future slides with graphs look better like that. So lock-free queues exist. The literature commonly references this paper, and I initially implemented it using a hand-rolled assembly instruction that doesn't exist in Go, which is necessary in this paper. But this instruction is double width compare and swap. It turns out that because I had to hand roll it, I could not hook into the runtime and have this write barrier pointer memory sanitizer stuff, and it completely corrupted everything when I tried to use it. But in a garbage collected language, we don't need double width compare and swap. We can just add to the queue, do some magic, dequeue. But if we don't rely on that, if we don't rely on decas, we have to rely on allocation. And allocating underneath the hood uses mutex, and it also allocates, so it's slower. But when it came down to it, this paper and all others that follow it assume a steady state of perfect enqueuing and dequeuing, meaning that we would never fall into a case where the queue is empty or the queue is full. Now, I simply do not believe that these queues exist in real life. There will be imbalances occasionally, and it's the transitions between the stable enqueue and dequeue concurrently case and the full and empty that are extremely detrimental in programs and are actually important to focus on. So, as per usual, our Lord and Savior Dimitri has a bounded, multi-producer, multi-consumer queue implementation on his website. The way it works is that enqueuers, so imagine you have a gigantic array, and each array slot has a sequence number. Enqueuers will race to grab the sequence number, and if one wins, it has unlimited time to modify the contents of the slot. And when it's done modifying it, it will set the sequence number for the dequeuers. So they'll all race, lock free, compare and swap, grab a sequence number. If it fails, it'll try grabbing the next one, and then release the slot when it's done. The dequeue operation operates roughly the same. So what happens, though, is that if the queue is completely full or completely empty, the in-queue will fail or the dequeue will fail and immediately return. And how do we handle this as a caller to in-queue? We do not want to blindly spin as that eats CPU, and additionally, Go routine spinning may not be preempted in this case, leading to a burning CPU core and program live lock. So we need to add blocking around this failure case. What I did initially was simply add a sync condition where every dequeue did a broadcast or a signal to the in-queuers, but this was incredibly heavyweight. I could not get a sync condition to have the type of performance characteristics I desired, so I designed my own block. At an incredibly high level, this slide has the pseudocode for fixing the last slide. If we fail at an operation, wait until we are notified that we should retry again. And the block that I designed, like the real meat and potatoes of everything that's cool behind this talk, I can't really talk about because it's all the code and it's way too complex. But the block I designed has a custom lock as well. So one of the problems with the sync condition is that, as I said, every dequeue must notify the in-queuers. And what I designed is a block that opportunistically tries to return if it thinks any operation could have happened or could be possibly happening, which kicks you out to retry in queuing. And this ends up spinning your code a little bit, but it also has the best performance or not the best performance, but it also has a good failure case where it will fall into blocking if it absolutely needs to. So we have our alternative. Versus channels, my implementation is tricky. It's not linearizable, because with Dimitri's, if something grabs slot 1, it could be kicked out before it actually modifies everything. Something could grab slot 2, the second enqueuer, and then finish and return first before the first enqueuer actually finishes. So we will dequeue the second returned enqueue before the second enqueue. So we haven't benchmarked a channel's contention yet, but we know theoretically that my implementation has good contention behavior. And lastly, we have no idea the latency characteristics of either. Anyway, let's bench. So I ran all my benchmarks on this random Go version, but that's about a month ago, so it's effectively Go tip. This was on a 48-core physical core server, and what I would do is I would take the time before enqueuing, send that time through the queue, and then take the time after enqueuing, and then before dequeuing, it was take the time before and after. So that we have sort of 6 numbers, and with this we can get the total enqueue times, the total dequeue times, the total time that messages are spent in the queue. And then, as with standard benchmarks, supposedly, I trimmed the top 0.01 and bottom 0.01% of timing so as to eliminate odd spikes that correspond to non-normal minimums from your kernel switching things out and scheduling. So what I would do is I spun up 100 enqueuers, 100 dequeuers. They all waited until everything was ready, closed a channel to start them all, and then they ran this. And if you look at this, this is sort of a little bit ugly to look at. I made this with some Linux utilities, so I mean, you get what you pay for. But channel are the red ones. The custom npmc with the block are my blue ones. And what you see is that my throughput timings generally sort of have lower times than the channel ones. My npmc ones have lower timing. But you also see that they have terrible worst case scenarios. All of these graphs have logarithmic scale because once you fall into blocking, the performance just like falls off the chart. So we're already sort of beginning to see that predictable latency is not a thing. So this is how long they spent in the queue, and then if you look at in-queue timings and dequeue timings, it's sort of the same. You know, it's in this case, my implementation was slightly slower, but we'll investigate throughput later. So with 100 enqueuers and 1 dequeuer, you can sort of ignore the yellow one for now. It's a little bit much for this talk. But you see that my implementation is faster, 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 and when it comes down to it, the box plots actually have somewhat predictable latency on the stable state, but again, the upper 20% just falls off the chart, or upper 25%. And then with 1 enqueuer and 10 dequeuers, again, sort of all over the place. The point is just to hammer home, like, we're comparable, you know. 1 enqueuer, 1 dequeuer, my performance is still actually pretty phenomenal in this case. I have pretty tight latencies at the bottom, but what now? Time was not necessarily more predictable. My implementation did have some tighter bounds in the quartiles, but as I said, falling into blocking in either the channel or the npmc implementations kills the bar graphs, or the quartiles. It's not unreasonable to include the block timings because, as we saw, both enqueuing and dequeuing fell into blocking, which effectively proves there is no stable state at all that all these papers explicitly test around. So my channel implementation, implementation versus my implementation both have unpredictable latency, solely due to the necessity of blocking. The core of everything that I've done, everything I wrote my abstract on, and all the research that I did was effectively wrong. But all is not lost. If we look at throughput at 48 cores, and at 48 cores it sort of holds true for all fewer cores. My implementation had a higher throughput for enqueuers and dequeuers in all cases across the board, sometimes dramatically. But the caveat is my implementation eats your CPU. So we have poor latency, we can't do anything about that, but I did get a different, unintended, better, what I was talking about earlier, the higher throughput. And as I mentioned though, my implementation eats CPUs, so channels are better there, but as I said, what even is better, it really depends on your use case. high throughput may be of the utmost importance. And really, when I think of it, in code I generally designed, I want higher throughput than I do more predictable latency. Internally, somebody else at the company would like to debate me on that, but whatever. So at this point, I sort of have to ask, is predictable latency even possible? I have my doubts. All research papers benchmarking this latency with lock-free and wait-free queues all force some stable state with their queuing system. I really doubt that in a real-life scenario, anything will be predictable. The temperature of your CPU will affect the speed, all the way through the kernel having scheduling behavior, to the Go scheduler being not predictable as well. But everything I've done shown that there could be alternatives. We can get higher throughput if we sacrifice some other things that we may not need in our implementation. So what now? Everything I've done shows there are subtle ways to use code that could lead to subtle performance and characteristic changes. But I'm not even sure if that one benchmark I wrote subtly favors my implementation, masking the fact that channels may still be better than everything I've done across the board. I'm not even sure if anything that I've done would be beneficial in a real system, although I'd like to think that, and at some point I'm probably going to use all of this code, hopefully, I pray. But I have shown that alternatives are possible, and I'd like them to be easier to design and implement. So what I'd like, this is sort of a little mini ranting session. The Unsafe package is still relatively ambiguous. I think it could definitely use with some clearer documentation, even though they've sort of been improving that in the last, I don't know if it was 1.5. What I'm doing in my implementation isn't exactly specified, but reading between the lines and looking at the Go runtime seems to imply that what I'm doing must be safe. The Go runtime would seemingly fall apart if it's not. Additionally, I'd like some documentation on instruction reordering. There is nothing in the docs about it, nor the atomic docs, and it's mentioned in passing in the memory model, but not in the reordering way. So there was a thread asking about this on the Golang dev mailing list, which Rob Pike concluded by saying that the atomic package is simple and clear and well documented. But that does not address the fact that simple and clear still does not actually tell you how instructions will be reordered by your CPU. When you work low level enough, you need to know if what you're doing will work. And without the definition, we have to assume that we have the strongest definition. So when you use the atomic package, if you load, this is too low level. It'll do a barrier, so it'll force it to load right there, in a way. Whereas you can sort of have relaxed atomic loadings that this load can get reordered around the other surrounding code. In C++ and Rust, there are six ways of guaranteeing order and loads. In Go, it's one. And it must be the safest of those operations at all times. As I just mentioned, C++ and Rust have 6 ways of specifying atomic loads, modifications, and stores. We don't need all of them, but if we have a few more ways to control how the CPU reorders instructions or not, we can get some serious benefit in speed, latency, and CPU behavior. All these new functions would be pretty ugly. We'd have to have a few new functions for each of our current compare and swap, atomic load, store, and whatnot, for each of the types. So it'd end up being over 100 new functions. It'd be pretty ugly, huge API, but it would be easy and intuitive to use, and in my opinion, it would require less documentation while being more explicit than the current atomics. It's not pretty, but it would be simple. Most of the atomics in my code I wrote earlier, all this npmc and blocking, can be swapped out for weaker atomics, which would actually increase my throughput even more. I would argue that multi-core programming is complex today because programming has historically been single core. Now it's sort of niche to program on a purely single core machine. We haven't needed to think about the weight of our synchronization primitives because even at a few cores, standard mutexes are mostly fine. But as cores explode, and they will, it's no longer acceptable to use the heaviest synchronization primitives at all times because everything else is too complex. It's complex only because we haven't dealt with it, but we're sort of in a situation where we're not dealing with it because it's too complex. So how do you rectify that? Anyway, in summary, real short and sweet. Go is good. Channels are phenomenal. I cannot really design a predictable latency system, and odds are, in almost every case that you'll ever run into, channels will solve your solution. But idioms can be broken. So you can use Unsafe and you can use assembly when you really need to, and it could provide you great benefits. And then my final slide, it's a little bit ranty, but it should be easier to create alternatives to idioms. Anyway, thank you. That's my talk.